Earlier on, we learned about the photoelectric effect. Now, it's been a little while since we've learned about that, but you guys remember the gist of it, right? When light strikes a metal, sometimes an electron will be ejected. And Hertz tried to explain it, couldn't. Einstein comes along and says, no, it's a photon of light. Light's a particle called a photon, and a photon of light strikes the metal, and if that photon has sufficient energy, then an electron can be ejected. We've done all the math with that. We're not going to go back and revisit that today. But I wanted to remind you what the photoelectric effect is to introduce you to this new topic called the Compton Effect. Compton Effect says, look, you got a photon that strikes a metal. If that photon is energetic enough, like let's say it's an X-ray photon, not just an ultraviolet or visible light or whatever. Let's say it's an X-ray photon, which is really, really, really energetic. Like crazy energetic. It strikes a metal, and sometimes an electron's ejected. But not only is the electron ejected, but sometimes there's a second photon ejected as well. So picture this. Photoelectric effect. The photoelectric effect says, here's your photon. It strikes the metal, an electron gets ejected. Okay, the Compton effect says, here's your metal, here's your photon, strikes the metal, an electron is ejected, but there's also a second photon ejected as well. So the difference here between this and the photoelectric effect is that you got a second photon, not just the photon that struck it, but a photon that comes out of the metal as well. But what's neat about this is that it's not just the photon that struck it reflecting, it's a different photon. If an X-ray photon of 10 to the 19 hertz strikes this metal, then an electron's ejected, and then another photon that might be 10 to the 18 hertz is ejected as well. It's a different photon with a different frequency and a different energy. Now, classical theory is old physics, right? Pre-quantum theory, basically pre-20th century physics, suggested that if there was a second photon ejected, it should just be the same as the first one. If an X-ray photon of 10 to the 19 hertz strikes the metal and we get an electron ejected and a photon ejected as well, the photon should be the same photon as we had to begin with. But that didn't work. That didn't match the observations. That photon, again, that second photon was less energetic than the first. So Arthur Compton comes along, 1908, I believe was the year, although that's not critical, comes along and says, I can explain this. I got it figured out. It's like Einstein came along and figured out the whole idea of the photoelectric effect. Compton comes along and says, I know why that photon is less energetic, because this photon that strikes the metal, this X-ray that strikes the metal, causing an electron to be ejected, that's really a collision between a photon and an electron. And in a collision, we have to have the law of conservation of energy and the law of conservation of momentum hold. Those two laws must hold. Therefore, this photon that struck the metal must have momentum. You can't have momentum conserved if you got momentum of the electron after the fact, but no momentum going into it. The photon that struck it must have momentum. The electron that's ejected has momentum, and the second photon has momentum as well, but less momentum and therefore less energy than the first one, because the electron took some of that energy and momentum away. So what's the big takeaway from this? Well, the really big takeaway from this for us in Physics 30 is that photons have momentum. And that might not right now seem like a really big deal to you, but if you take a step back from it for a second, what's the equation for momentum? What equation did we learn back in Unit 1, back in September for momentum? Yep. P equals mv. Good. What's the mass of a photon? There is none. So how can photons have momentum when there is no mass, and momentum is mass times velocity? Well, Compton derived a couple equations that describe the momentum of a photon. I'm not going to go through that derivation for you. It's on the note in the notes that I photocopied for you. You're not going to have to derive that equation. Okay, if you're confused by that, if you're interested in how these equations come about, then I can help you out with that. But in the interest of saving a little bit of time, I'm going to give you those equations. Those equations are the following, and these all appear in the top right-hand corner. This one is not new, right? E equals mc squared. This is where these equations that Compton derived come from. These are the new ones. P is equal to h over lambda. The momentum of a photon is equal to Planck's constant over the wavelength of a photon. Notice it's not related to mass. It's actually related to equivalent mass, right, which is related to energy. So in other words, this equation comes from the energy mass equivalence principle of Einstein, E equals mc squared. We're just not going to worry about exactly where that comes from. Now, Planck's constant here, you always want to make 6.63 times 10 to the minus 34 joule seconds. Okay, always. Don't do the electron volt thing ever with photon momentum. Now, this other equation that Compton came up with says E is equal to P times C. The energy of a photon, which, by the way, we know the energy of a photon is HF. We also know the energy of a photon is hc over lambda. Now we're relating the energy of a photon not to the frequency and wavelength, but we're relating the energy of the photon to the momentum of the photon. The momentum of the photon times the speed of light. So two new equations that describe for us the momentum of a photon. Finally, here's the last equation you do in Physics 30. The very last one. The doozy, though. Delta lambda is equal to h over mc times 1 minus cosine theta. H is Planck's constant. We always want to be in joules here, 6.63 times 10 to the minus 34 joule seconds. We're talking about an electron being scattered here. So the mass is going to be the mass of the electron, 9.11 times 10 to the minus 31. C is the speed of light. And theta is going to be the scattering angle of the photon, the angle at which the X-ray scatters. And of course, that's going to be in degrees. We never use radians, right? Always degrees. Delta lambda is the change in wavelength of the photon. Now think about that. The photon struck the metal. An electron was ejected. A second, less energetic photon is ejected as well. If it's less energetic, then there's going to be a change in energy. But there's also going to be a change in frequency and a change in wavelength as well. So this is going to be the change in wavelength of the scattered photon. The photon loses energy, therefore the frequency of the photon decreases, the wavelength of the photon increases. It's an ugly looking equation, but you know what, it's not all that bad. It's not all that hard to use. And the good news is you don't have to memorize it. It's on your data sheet with the rest of these equations in the top right hand corner. So listen, before we do a couple examples here, remember this. If you get a question that we got back in Unit 1, back in September, that asks you for the momentum of a car, the momentum of a train, the momentum of a baseball, the momentum of a proton, then use m times v. Because all of those things have mass. And whenever you're trying to find the momentum of something with mass, you're going to use P is equal to m times v. It doesn't change anything from what we've learned so far. But if you're dealing with the momentum of a photon, of a particle without mass, radio waves, gamma rays, X-rays, then the momentum of the photon is found by one of these equations. P equals h over lambda, E is equal to P times C. Delta lambda is equal to h over mc times 1 minus cosine theta. Does that make sense? So remember what the Compton effect is, the idea that it's not just an electron ejected, but it's an electron and a second less energetic photon ejected. But again, the big thing that we're going to have to deal with here is the momentum of the photon. Now, I told you that these two equations in red here were basically derived from these two equations. P equals mv and E is equal to mc squared. Here's the question that I've seen a few times over the years. Where is this one derived from? Don't even ask me how to derive this one. I've tried to derive this one and I can't do it. But it comes from conservation of energy and conservation of momentum. Somehow, if you put those two together, you'll end up getting this, in the context of photons, you'll end up getting this equation. They're not going to ask you how to derive it. I can promise you that. But they may ask you where it comes from. And the answer is the law of conservation of energy and the law of conservation of momentum, if they ask you that question. And like I say, I've seen it maybe, not a lot, maybe 3 or 4 times over the years, enough to make it worthwhile talking about. Here's our first of 2 examples. It says calculate the energy and the momentum of a photon whose wavelength is 600 nanometers. Well, prior to today, you could have done half this question. The energy of a photon, this one's easy. The energy of a photon is simply equal to hc over lambda. If we want to find the energy in joules, then we're going to say 6.63 times 10 to the minus 34 joule seconds. If we want to find it in electron volts, then we'd use the other value, 4.14 times 10 to the negative 15 electron volt seconds. Multiply that by the speed of light, 3 times 10 to the 8, divided by the wavelength of 600 times 10 to the minus 9. And I think when we do this, I think we get 3.315 times 10 to the negative 19 joules, which we would round to 3 digits, 3.32 times 10 to the negative 19 joules. You could find that in electron volts, or you could convert it to electron volts once you've got joules if you needed to do that. But what about the momentum of the photon? That's new. Okay, we could have done this for weeks, that first question. What about the momentum, though? Prior to 10 minutes ago, we couldn't have touched that. We would have saw this question said, oh, momentum. Momentum is P is equal to m times v, but we don't know, there's no mass of a photon, so we can't do that. We would have had no idea what to do. Now we do. You want to find the momentum of a photon now? Well, let's go back to those equations in the top right-hand corner of your data sheet. Which one are you going to use? H over lambda, E is equal to P times C, or I don't even see momentum in here, so probably not that one. Tell you what, either one in red would work here. Ethan, which one do you want to try? That's probably what I would do too. Remember to use 6.63, always use the joules for this one. Now, could you have used the other one? E is equal to P times C? Sure, we just solved for E, right? We know what C is. We could have solved for momentum using E is equal to P times C as well. So either one would work there. I probably would have went with this one, Ethan, just in case I made a mistake on this, right? What is 6.63 times 10 to the minus 34 divided by 600 times 10 to the minus 9? 1.105 or 1.11 times 10 to the minus 27. Now this is a little bit weird here. 10 to the minus 7, 27, what are the units? What were the units for momentum? Kilogram meters per second. It's weird to talk about units of kilograms meters per second when photons don't have any mass. But remember what they do have. They have energy. And remember that energy and mass are kind of equivalent, right? And they're not exactly the same thing. It's like ice and water. They're not exactly the same thing, but they're 2 different forms of the same thing. So it's not that far-fetched to talk about momentum of a photon talking about kilograms as a unit. That's a good question. Could you also use joules seconds over meters? Yes, absolutely you could. 1.11 times 10 to the minus 27 joules seconds over meters, and that of course comes from this, right? In fact, even if we look back to what we did in September, like that would even be a valid set of units for that now. It's just that it's a lot less common, that's all. It's always valid. Anything you can get legitimately from an equation is always a valid set of units. I'd like you guys to take a look at a couple of questions here for the next couple of minutes on page 723. See what we can do with those. over the next few minutes. Then we'll do one more example, and then we're done with the Compton effect. Okay, let's take a look at number 3. It says if a 10 nanometer X-ray scattered by an electron becomes an 11 nanometer X-ray. Wait a sec, the wavelength went up. Didn't we say that the second photon would be less energetic than the first photon? Yeah, we did. If energy goes down, then wavelength goes up because E is equal to hc over lambda. How much energy does the electron gain? What a lot of people want to do for question number 3 is say E is equal to hc over delta lambda. Can you do that? No, you can't. You can say hc over lambda twice. Do it for the 10 nanometer photon, do it for the 11 nanometer photon, and then subtract them. Delta E is equal to the energy of the 11 nanometer photon minus the energy of the 10 nanometer photon. You cannot say hc over delta lambda, and you can't say that because delta lambda is on the bottom. If it happened to be on the top, you could get away with that, although I wouldn't suggest it. But on the bottom, because it's not a direct relationship, you can't do that. So get the energy of the first one, get the energy of the second one, and then just subtract it. If you're looking for the momentum gained or lost, or in this case it would be lost, I guess, then you would say P is equal to H over lambda, P is equal to H over lambda, and then subtract the P's, the momentum. Okay, I want to give you another example now. This one's using that other equation, that ugly looking equation. Okay, let's go back here. Just a request to do this. We're going to say HT over lambda. We're going to say this is 6.63 times 10 to the minus 34 times 3 times 10 to the 8. Divide it by 10 times 10 to the minus 9. And let's figure out what we get there. 6.63 times 10 to the minus 34 times 3 times 10 to the 8. Divided by, do some brackets here, 10 times 10 to the minus 9. 1.989 times 10 to the minus 17. We'll do the same thing right here. This is going to be 6.63 times 10 to the minus 34 times, this time it's 11, it's still 3 times 10 to the 8, I guess. Divided by 11 times 10 to the minus 9. 1.80818 times 10 to the minus 18. So let's subtract those now. And we end up getting 1.81 times 10 to the minus 18. Is that okay? Okay, let's go back to this one now. It says an X-ray photon 0.0500 nanometer scatters at an angle of 30 degrees. What's the wavelength of the scattered photon? Well, we know that delta lambda is equal to h over mc times 1 minus cosine theta. By the way, we also know that delta lambda, although it doesn't say it on my data sheet, it's lambda f minus lambda I, right? Delta anything is final minus initial. Let's go to this equation though here first. Clearly this is the one we're going to use. 6.63 times 10 to the minus 34 divided by the mass of the electron times the speed of light times 1 minus cosine 30 degrees. 30 degrees would be the scattering angle of the photon. Okay, let's do the math on this one. Let's say 6.63 times 10 to the minus 34 divided by brackets 9.11 times 10 to the minus 31 times 3 times 10 to the 8. Okay, now let's multiply that by, make sure you use brackets here for sure, 1 minus cosine 30. I get 2.10 times 10 to the minus 12. Sorry? What did I do? Oh, shoot. 1 cos 30 should be 1 minus cosine 30, right? So let's say 1 minus cosine 30 gives me 0.133. And now it's going to be this number times that, right? 2.425905 times 10 to the negative 12. 3.25 times 10 to the minus 13. Is that right? Is that better? Oh, wait a sec, that's not my answer though. What do I got to do to find the answer? The wavelength of the scattered photon. What have I just found? Change in wavelength, I'm looking for final. So let's say delta lambda, which I just found, is equal to lambda f minus lambda I, which I already knew. So lambda f becomes equal to the number that I just got, plus 0.05 times 10 to the minus 9, 0.05 nanometers. That gives me my final wavelength. All right, if you're good with those, let's take a look at this one single question, please, on page 724. Remember, sometimes you're looking for delta lambda, the change in wavelength. It's always going to be a decrease in energy or an increase in wavelength. This time, as it was in the example, you're looking for the final wavelength, so lambda f. So you can do exactly the same thing as we did in the example question. Okay, let's have a look. What's the wavelength of the scattered photon? Look, we know when we're talking about photon scattering, photon momentum, we always look to the top right-hand corner of our data sheet. P is equal to h over lambda, E is equal to P times C. Those aren't going to be helpful to me in this case. They're valid, but they're not helpful. Delta lambda is equal to h over mc times 1 minus cosine theta. That's the one that's going to be helpful to me. Let's find delta lambda, and then we'll worry about finding the final. 6.63 times 10 to the minus 34. Always use the joule seconds one. Divided by the mass of the electron times the speed of light, times 1 minus cosine 90 degrees. What's cosine 90? This one's a little bit easier, actually. What's cosine 90? 0. Cos 90 is 0, so it becomes this times 1. 1 minus 0 is 1. So all I have to do really is figure out what this number is out front, which, I mean, it's always the same thing out front. 6.63 times 10 to the minus 34 divided by, use brackets on the bottom, 9.11 times 10 to the minus 31 times 3 times 10 to the 8. Now, technically, we have to multiply that by 1 minus cosine theta, but since cosine theta is 0, 1 minus cosine theta is 1, then it's just this times 1. There's delta lambda, 2.4259 times 10 to the minus 12, is it? Now, lambda f is going to be simply delta lambda plus lambda I, which is what I just got, plus 0.010 times 10 to the minus 9 meters. Is that okay, Julie? All right. If we're good with that, then I want to make a little summary, a quick little summary table here. Nothing new, but a quick little summary table to lead you into the next 2-minute blurb here. Okay? We have a number of things that tell us, that provide support for the wave theory of light, and a number of things that provide support now for the particle theory of light. I'm going to list those things, put little check marks where appropriate here. We've got refraction. Remember, way back at the beginning of the EMR unit, we said refraction provided evidence for the wave theory of light. Diffraction. Wave theory. Interference. Wave theory of EMR. Polarization. Remember, these were the first 4 that we learned. That very first day we looked at EMR way back before Christmas. Wave theory. Photoelectric effect. That provided evidence for the particle theory of light, because remember, it was photons. Photons are what correctly explained the photoelectric effect. Now, the last thing that we'll look at here is the Compton effect. Or, remember what the takeaway from the Compton effect was? Photon momentum. I think it provides evidence for the wave theory or the particle theory. Yep. Yeah, particle theory, absolutely. Now, I give you that little summary now because what I want to talk about next for just a couple of minutes relates to this, but is opposite to this in a sense. If EMR, if EMR in general, visible light, gamma rays, radio waves, whatever, if EMR in general can be both a wave, it used to be thought to be a wave, right? But now we know it can be both a wave and a particle, then why can't things like electrons be both a wave and a particle as well? If a wave can be a particle, then why can't a particle be a wave? We alluded to this a little bit when we talked about the Schrodinger or electron cloud or the quantum mechanical model of the atom. The electron travels around the nucleus in a wave. Well, de Broglie, it looks like de Broglie, but it's pronounced de Broglie. About 80 years ago or so, came up with a theoretical argument that said electrons or anything small like that, that we think of as a particle, also have a wave nature. That's it. He derived an equation that described the wavelength of an electron. You can actually calculate the wavelength of an electron. We don't have to do that, so we won't. He didn't have any evidence to support it, but it did come later through electron diffraction experiments. I think I showed you guys a video. Did I show you guys the cartoon video, the 5-minute cartoon video? The crazy one? Yeah. That's electron diffraction. When we have two openings like this, and when light goes through it, we would expect an interference pattern. But with electrons, we would expect just a bright spot here and a bright spot here where the electrons are going through. But what do we get? An interference pattern. So electron diffraction experiments give us an interference pattern, and that only happens with waves. So electrons have got to be waves in addition to being particles. Now, don't worry about the whole, you observe it, it becomes a particle again, and that's way beyond what you guys need to know here. What do you got to remember here, basically? The guy's name, de Broglie, or de Broglie, if you want to think of it that way. Particles, wave nature, electron diffraction experiments, done. Good enough.